students! In this video, we need to talk about Charles and Gay-Lussac's law. So first, we have Charles' law, and that's a relationship between temperature and volume for gases. So first, who thought this up? Well, it was this French physicist named Jacques Charles, and he was around in the 1700s and the early 1800s, and he was one of the first to conduct a scientific balloon flight. So he went up there and he gathered data for whatever experiment he was doing at the time. And whiz bam bang, he thought up some good information for us to learn in class. Keep me employed. So here it is. What Charles said is, if you fix the pressure, the volume of the gas is proportional to the temperature of the gas. And remember, with Boyle's law, we had inverse proportionality. So when one thing went up, the other thing went down. Now, direct proportionality is where we have one thing increasing and the other thing also increases. So if you increase the temperature, you're also going to increase the volume. So see right here, we've got gas at minus 65 degrees Celsius. So that's really cold. So the gas molecules are trying to get really close and snuggle and not take up a lot of room. And then if we give them a lot of heat, they're going to start moving around, and that takes up more space, and they're going to be bumping into each other, and they're going to be hitting the sides of the container more often. And if there's a part of the container that will move, the bumps on that part of the container will expand the container, and we'll see that the volume will increase. So if we have a temperature increase, we also have a volume increase. And if we have a temperature decrease, we also have a volume decrease. So if one thing goes up, the other thing also goes up. And if one thing goes down, the other thing also goes down. So again, they're directly proportional. On this slide is where we start with the math. Boo! But here's Charles' equation. So remember, Boyle's equation was P1V1 equals P2V2. Well, with Charles's equation, the pressure is kept constant. So we don't worry about the pressure. And what we're changing is the temperature. And because they're directly proportional, the temperature goes into the bottom, and we get this equation right here. So we have V1 over T1 equals V2 over T2. And we're going to have to work problems where we have three of the variables and we've got to solve for one of them. So if you're not feeling like doing the magic of algebra that day, you can just look right here, and I've solved for all of the different variables for you. And we want to remember one thing, that is all of your temperatures need to be in Kelvin. Kelvin, Kelvin, Kelvin. So if you don't remember how to get to Kelvin from Celsius or Fahrenheit, review that information. So if we're going to look at this picture right here, what we'll notice is when you double the temperature, so we go from 200 Kelvin to 400 Kelvin, what happens to the volume? Well, that also doubles. So you guys can see the direct proportionality there. When you double one, the other one's going to double. In the other direction, if you half one, so if you go from 400 Kelvin to 200 Kelvin, you will also half the volume right there. So again, direct proportionality, and we're keeping the pressure constant. Now let's take a look at this picture, and I'll come back to the graph in a second. So if we were to take a balloon and put it in a cold situation, what's happening is that the gas molecules don't have much energy. So they start moving around really slowly, and they start snuggling together. And so that space between the gas molecules is a lot less, and they aren't hitting the sides of the container as often. So we can see how the volume is decreasing there. And then if we heat it up, we're giving the gas molecules a whole lot of energy. And so they're bouncing around and they're hitting the sides of the container. And like we said on the other side, wherever the container will expand, it's going to expand. And just to reiterate this, we can see down below if we put a balloon in liquid nitrogen, which is 77 degrees Kelvin, or 77 Kelvin, excuse me, and that translates into negative 195.8 degrees Celsius, or negative 320 degrees Fahrenheit, we can see that that balloon will contract a whole lot because those molecules, those gas molecules inside the balloon are like, whoa, it's super cold, we have to snuggle. And then on the other hand, we have this picture over here showing a hot air balloon. Now the reason the hot air balloon is floating is because we're heating up the gas molecules that are inside the balloon, and when we do that, we can see that they expand. So what's happening inside the balloon is that the air in there is becoming less dense. And when something is less dense than something else that it's in, what happens to that stuff that's less dense? And think oil and water, or a wood boat in water. It floats. So the less dense air in here floats in the more dense, or the denser cold air out there. So that's what's going on with our hot air balloon. Now if we graph this, what we'll see here is our direct proportionality. So as we increase the temperature, we also increase the volume. And you can see that with the pictures right here. Increase the temperature and you increase the volume. Those molecules are moving around a whole lot faster and taking up a whole lot more room. All right, on to some math. Yay! So we got some problems here. And problem number 1 says you've got a cylinder that contains 5 liters of gas at 225 Kelvin. If the temperature is increased to 345 Kelvin, what will the new volume be? Okay, so let's just look at what we've got. First of all, we've got 5 liters of gas and we're at 225 Kelvin and we're going to heat it up. So do we expect the final volume to be greater than 5 or less than 5? No math yet, just thinking about we're heating up this gas. Should be greater than 5. Now, if we are looking at identifying which equation that we need to use, so say we didn't know we were in the Charles law section and we didn't know what the equation was, what we would say is, okay, I've got 5 liters here, so that's a volume, and I've got 225 Kelvin, that's a temperature. And then I'm going to increase the temperature to 345 Kelvin. So that's another temperature. So if I've got 2 temperatures, we must have temp 1 and temp 2. Now, T1, the volume that goes with T1 has to be V1. And then the question says, what will the new volume be? So obviously we're asking for V2. So let's just go ahead and list our variables so we can visualize what we're thinking. So we've got V1, T1, V2, and T2. Now remember I said the math for this chapter isn't that hard. It's all of the different equations and remembering what you're doing. So Charles' law is V1 over T1 is equal to V2 over T2. So just go ahead and write that out for yourselves, because the more times you write it out, the more it gets in your brain and the quicker you get with these problems. So let me go ahead and erase that so I have some room. And then we're going to identify V1, which we already did, and go ahead and write it here. So we've got 5 liters and T1 is 225 Kelvin. V2, what is V2? We don't know what V2 is. We're solving for V2. And T2 we said was 345 Kelvin. Okay, so we're solving for V2. So let's go ahead and write the equation again, because the more times we write the equation, the more it gets on our head, and that's awesome. So we're solving for this variable right here, so we have to get it by itself. And we can multiply both sides by T2 and then cancel out the T2s on the right-hand side. Or you can just do the magic of algebra, which is that things can move diagonally across an equal sign all day long, and it's completely legal. And that would give us V1 T2 over T1 equals V2. And then we're just going to switch that equation around, because most of us like the variable that we're solving for to be on the left-hand side, and it's exactly the same thing. You'll get exactly the same answer. Oops, bad teacher, bad. Excuse me. There we go. And now we need to just plug and chug. So V1 is 5 liters. And T2 is 345 Kelvin. Now be very careful at that point, because what your brain's going to want to do is your brain is going to want to do V1 T1, but it's not correct. We have V1 T2. So be careful there. That is an extremely common student mistake. And on the bottom we have T1, which is 225 Kelvin. And we have to take a look at that and say what cancels out, and that's Kelvin, because anything divided by itself is what? Is 1. So Kelvin divided by Kelvin is 1. So we put this into our calculator. 5 times 345 divided by 225. And we have 3 sig figs, 3 sig figs, and 3 sig figs. So our answer is going to be in how many sig figs? 3. And what we have is 7.67. And our units are what? Liters. There we go. And then we put a nice circle around our answer so our professor can find it in order to grade it quickly and give us all our points. Now, number 2 says a ball contains 3 liters of air at 32 degrees Fahrenheit. If the volume increases to 5 liters, what must the temperature have changed to? Now, before we do any math on this one, let's just think about what we're looking at. We've got a ball that has 3 liters of air inside, and it's 32 degrees outside. So that means it's freezing. If the volume increases to 5 liters, what did the temperature have to change to? So is that going to be a decrease? Is it going to be getting colder? Or is it going to be an increase? Is it going to be getting hotter? It's going to be getting hotter, because when the temperature goes up, the volume also goes up. So if it went up to 5 liters, it must be getting hotter. So let's go ahead and list our variables so we can organize our thoughts. So we have V1 and T1 and V2 and T2. V1 is what? 3 liters. And T1 is what? 32 degrees Fahrenheit, and we're going to need to change that to what? To Kelvin, because that's what the gas laws say we have to do. And V2 is 5 liters, and what's T2? We don't know. That's what we're solving for. Okay, so first of all, what we're going to need to do is we're going to need to change T1 into Kelvin. Now, 32 degrees Fahrenheit, that's a special temperature. That's the freezing point of water. So this one should be a little bit easier. We don't have to whip out the equation for switching from Fahrenheit to Celsius, because we should know at this point what the freezing point of water is in Celsius. And what is that, you guys? That's 0 degrees Celsius. Now, going from Celsius to Kelvin is really easy. We just add what? 273. So 0 plus 273 is what? 273. So we have 273 Kelvin there. Okay, so now we need to solve for T2. And T2 is on the bottom, so this is going to take a little bit of work, even doing the magic of algebra. So we've got V1 over T1, which is equal to V2 over T2, and we need to solve for T2. And in order to solve for T2, we need to get T by itself and on the left-hand side of the equation and in the top. So we take T2, and with the magic of algebra, we can say, well, it can move diagonally across the equal sign. So we can put it up there, and that allows it to be in the top, but still not by itself. We need to get rid of V1. And let's go ahead and switch colors here and circle V1. And V1 can move diagonally across the equal sign, so it's going to go down to where T2 was in the first place. But then we've got T2 on the top and T1 on the bottom, so T1's got to go. So we can go ahead and we can move T1 up here. Now, like I said, you guys, you can do this with the traditional algebra way, but the magic of algebra might save you a little bit of time and help you visualize what's going on. And we find that T2 is equal to V2, which didn't move, it stayed there, times T1, because T1 went diagonally across the equal sign up to visit V2, and V1 moved down into the denominator. Now all we have to do is plug and chug. So we have that T2 is equal to V2, which is 5 liters, times T1, which is 273 Kelvin, divided by V1, which is what? Which is 3 liters. Okay, so what is canceling out here? The liters. Good. Okay, so we do 5 times 273 times 3, and what we're going to get is we're going to get 455 Kelvin. But if you go to look at the answer, if you're doing the book problems and the homework, the answer most likely will not be in Kelvin because the first temperature was given to you in Fahrenheit. So what we expect you to do is turn that back into Fahrenheit for the answer. And we know how to do that because we went through all the math in chapter 1. And getting from Kelvin to Fahrenheit, we should go through Celsius. And getting from Kelvin to Celsius, we need to subtract what? 273. So over here, what we did when we were going from Celsius to Kelvin was we added 273. So in order to go from Kelvin to Celsius, we got to subtract 273. So that is going to give us 183 degrees Celsius. Now we're not quite done yet. We got to get back to Fahrenheit. And when we go to Fahrenheit, from Celsius, we're going to multiply by 1.8 and add 32. So we've got 183 times 1.8 plus 32. And what we're going to end up with is 360 degrees Fahrenheit. So if the volume of your ball switches magically from 3 liters to 5 liters, it looks like it might not be a very good day for humanity there. Woo, that's pretty hot. Okay, so I've been telling you guys how with the gas laws you need to be in Kelvin. And I haven't quite gone into the explanation of why just yet, but I want to show you by backtracking to number 1 why we can't just leave our temperatures in Celsius when we do our calculations. So let me go ahead and erase number 2 so I have some room to redo number 1 over here. Okay, so if we don't use Kelvin, what we would have is let me switch over to down here. What we'd have is V1 is equal to 5 liters, and we would have that our temperatures are going to be in Celsius. So we would have negative 48 degrees Celsius for T1. We're solving for V2, and T2 would be 72 degrees Celsius. So I was just changing these guys right here by subtracting 273, because that's how we get from Kelvin to Celsius. Now you guys can see that we've already solved for V2 in these 2 spots, so we would just need to plug and chug with our new Celsius temperatures. So we would have V2, and I'm just plugging and chugging with that equation right there. And V1 is 5 liters. And then we have T2, which is 72 degrees Celsius. And then we have T1, which is negative 48 degrees Celsius. And the Celsius, excuse me, cancels out. And our answer is negative 7.5 liters. Now, I don't know about you, but I don't know how we get a volume of negative 7.5 liters there. So you can see how keeping it in the positive zone with Kelvin, because Kelvin only has positive numbers and 0, it's going to give us positive volumes, which works out a whole lot better for us, because what on earth is negative 7.5 liters? Okay, so that's the reason why we're using Kelvin for all of our calculations. On to Guy-Lussac's law. So